Hello, everyone, and welcome to Life Science Cafe. My name is Chris. I'm a PhD student in the Organismic and Evolutionary Biology program at UMass Amherst, and I will be the MC today for astrobiologist Dr. Abel Mendez. Established in 2011, Life Science Cafe is organized by graduate student researchers at the University of Massachusetts Amherst. Each month, we invite different experts to discuss their research. Typically, we host these events in the Amherst community, but we are happy to continue our efforts virtually during this interesting time. We would like to thank our funders, the Organismic and Evolutionary Biology Program, the Graduate Student Senate and the Graduate School at UMass, the National Science Foundation, and our generous UMass Gives donors. For our next event, we will be discussing bees with Dr. Rosemary Malfi on October 29th. Subscribe to our mailing list and stay tuned for future cafes. For this event, we are excited, one, to host a speaker from outside the Western Mass area, and two, to talk about life science, not just on Earth, but in space. Today, we are so very grateful to have Professor Abel Mendez. He is a planetary astrobiologist and the director of the Planetary Habitability Laboratory at the University of Puerto Rico at Arecibo. He has worked with NASA at a number of different campuses, and his research now is at the Arecibo Observatory. His lab's goal is to map the habitable universe, that is, identify good places for life beyond Earth. Welcome, Abel, and thank you so much for being with us. How are you?
Oh, hi. Thank you for having me. It's a pleasure to be with all of you, virtually.
So do you want to start by telling us a little bit more about yourself, or we can jump right into questions?
Yes, I am Professor Abel Mendez and at the University of Puerto Rico at Arecibo. This is a campus nearby the Arecibo Observatory. It's not related, but we collaborate together. So my field is physics and astronomy, but I also do a master in biophysics. And one of my issues always is to connect physics, astronomy with biology.
Great. So to start, a big question we think of when it comes to space is there life on is there life out there? What does this play in your work? What role does this play in your work?
Yes, what we try to do in our lab is to connect astronomy and biology, specifically to find the connection with habitability. From, let's say, in this image here, what is the difference between the picture in the moon and the picture to the rainforest? What are the conditions and the environment that made this difference in terms of biology? So it is not obvious for Moon, Mars, and even in the middle picture, the terrestrial desert, that life is there. But in the dry forest and in the rainforest, life is totally present there. You can see it in your own eye. Even in the desert, there's microbial life. Maybe there's microbial life on Mars. But what environmental factors make this possible? So that's what we try to do, how to interpret these gradients of life in different planetary environments, starting from Earth as an example, then trying to apply that to planets in our solar system, including ocean planets, and then to exoplanets, planets around other stars.
So what exactly are you looking for? Can you give us a quick definition of life?
Well, I always like to have to present definition of life like a physicist. So in terms of physics and fundamentally, I can say that life is a biological machine, a natural machine. A machine in physics, it doesn't mean that it's composed of electrical components or that kind of stuff. It just means a system that takes energy from one region and moves that energy. So, and in this process, it generates heat. So I think that is as a fundamental, all life do that, like any machine. So, and then it has some features, like features like capacity to replicate itself, to evolve. So there's some particular features that you can assign to different life forms, and some are more robust than others. But fundamentally, it's like a natural machine made by nature.
Okay, so what is habitability? Does a planet need life on it to be habitable?
Well, that's a very good question because we think habitability is formally defined as the suitability for life or an environment. And one issue here is that, and we can talk through this through the biologists, because in astronomy, that's the term that they use for this concept, the suitability of environment for life. But if you look further in biology, there is a specific term for this habitability. It's not called like that. It's called habitat suitability. That's the formal term in biology and ecology, but it's the same thing. It's the same thing. So a good way to define this, and it's a very good comparison, what makes an environment habitable is the classical elements, air, water, earth, and fire, because more formally, gas, liquid, solid, and energy, because all life needs the three phases. And one of the reasons beyond the fact that we need flow is that the basic elements for the DNA are divided between gas, liquid, or solid. You cannot find a single phase with all the elements having a liquid water at the same time. And the energy source could be some by radiation, solar energy, but also could be chemical energy. So there are different sources for energy. So all life has to have these basic requirements in the environment. And in one particular phase, you need a series of elements.
Amazing. So why do we care if a planet is habitable?
So it's very important just to make sure that you have the right conditions for life on the planet. Let's say if you want to detect life, you want to make sure that life is not, if you want to explore the planet, you want to make sure that there is not life there, or you have to be more restringent to avoid contamination or cross-contamination. Also, for life detection, there are two things. There are biosignatures, detections of indication or markers of life, and habitability. And usually in terrestrial environment, you have those together. So places that are considered more habitable, they have more life. So that's the general pattern. So if you analyze an environment and determine that is more habitable, then you will expect to have, if you detect life, there to be more abundant. Otherwise, if that doesn't match, it's telling you something that's not like life as we know it. Let's say you find an environment that you say, well, this is not habitable at all, but then you try to search life anyway, and you detect some life. So that definitely is not life. So that's very important to have the terrestrial comparison. And that's a concern for everybody. Just, okay, why you are so focused in terrestrial life? You have to have that basis just to say if one environment is something related or not, like Earth. And I want to show you the application of the classical elements. And here is a rainforest. And the rainforest, you have a lot of wind, a lot of water, a lot of earth, and a lot of sunshine. And that's why you have life there present, very visible, and that life support, those plants support vegetation, support animals, and complex life, probably intelligent life. But it is amazing that a planet so habitable like Earth, you have something like this that looks like Mars. So in the dry deserts, the limiting factor is liquid water. In ice cap, you have also the limiting factor. You see a lot of water, but that water is as ice. So that's the same problem. I don't see vegetation adapted to that environment anyway. So life is so robust, but it has some fundamental limits when you go to the physics and chemistry of the available mass and energy for life. And in the clouds, I was expected maybe that clouds could be green because a lot of life there, but no. And the problem here is the earth, the dust, aerosols that go up in the sky that could provide some nutrients, but they tend to also fall down. So it is not a good environment for life. And that, and you probably, a few weeks ago, you heard about life on Venus. So if I was expecting life on Venus, I would expect a lot of life here also in the clouds, but it's more like a transient place for life. It's not a stable place for life. And ocean surface, I should expect a lot of vegetation cover all the oceans, water plants, but no, it also looks like a desert of life. And the problem is the same as the cloud. Nutrients fell down, precipitate. And that's why it's more like the farther you go from the coast, it's more like a transient place. It's not so good for abundant life, like a rainforest. But if you go deep to the oceans, then you may say, okay, then we have all the ingredients, but that is more limiting. The farther you go, the deeper you go, then you have less air dissolved in the water, and you have less light energy. So again, you have a desert of life. So the only place that we can say is more habitable in our planet. Habitable means here that is related to how much life it can support, more abundant. And usually that when you have more life, you have also the probability of having also a lot of diversity, like happens in the tropics. So it's rainforest. And the worst scenario here that you will find less life is the clouds. So that gives you an idea on how this simple connection of the classical elements can help you. If you find a planetary environment, just try to look for how much compared to Earth are these ingredients. And you then, okay, use that comparison, how much life it can support compared to Earth.
Okay, so really cool examples here on Earth. Other than Earth, where are you looking for life or for habitability? Are you looking elsewhere within our solar system? Are you looking at other star systems? Are you looking at moons?
Yeah, in our work, we try to explore more data from the solar system to make predictions of habitability and how that might tell you something about where to look for life. But I'm mostly interested now in exoplanets, planets and other stars.
Okay, so how do you determine if a planet is habitable? Basically, how do you do your research? How do you look at these planets, at these exoplanets?
Well, for planets around other stars, then we have three criteria. The first one is the planet has an habitable orbit. This only means that the orbit of the planet is within the habitable zone. So this is the zone where a terrestrial planet will be able to have an ocean. If it gets too close to the star, then to the red zone here, then the ocean will evaporate. If it gets too far, it will become ice. So there is a region, but that works for the planet. It has to have the right size. So that's the next criteria. It has to get a habitable size. So what habitable size? For planets like Earth, that will be about half the size of like Mars. So the problem with Mars is that is too small. And once you get about half the size of Earth, it's very hard for a planet to keep an atmosphere. But if you go higher into that, that sounds good because you will trap more atmosphere. It sounds like you will have more mass available for life. But the issue is that then you will have too much atmosphere, and even if you have liquid water at the surface, it will become ice, no matter the temperature. So even if the planet is just 1% atmosphere, just 1% atmosphere, the total mass, then any water at any temperature will become just solid. And then you need the liquid water. So, and here I go up to 2.5 Earth gravity. That's the limit is for ocean planets. If you're thinking more like a terrestrial planet, so maybe it's just 0.5 to 1.5 Earth gravity. And this is also, you can tell the same thing in terms of mass. And so we select from the different discoveries of different planets detected elsewhere by different observatories. We take that sample and I filter these planets just by these criteria, 1 and 2, and to tell if the planet is potentially habitable. And then we have to stress out that it's potentially habitable because these are only the factors we can see. We want to see more of the planet, how much water. This is not telling you how much water it has. It's telling you how good is that atmosphere or the ingredients. So this is only the things that we can measure, the orbit and the size. And we also go to the next step is that we sort this planet with what we call the Earth Similarity Index. This is a sorting, this is like sorting by 2 columns at the same time. So sorting by orbit and sorting by size, which are closer to terrestrial values. So that's the process of not only by determining which planets are potentially habitable, but also sort them out on which are closer to terrestrial conditions based on things that we can measure.
Okay, so you look at these planets. How many are out there that are potentially habitable, do you think?
Well, we keep, since 2011, we keep the potentially habitable exoplanets catalog. So this catalog was created at that time with just 2 or 3 candidates. So I question my sanity of creating a catalog with just 2 planets, thinking that maybe it will take so long to discover more, but no, it was a good idea because in the following years with 3, 4, and now I lost track of the number. Well, total number is 55, and here are just a few of those, the best ones. But total number is 55, but I lost track of the names of each system. So you can see the planets here. This is Jupiter, Neptune, Earth, and Mars for comparison. And all these pictures here, they're artistic representations. We cannot yet look at these planets, even like a dot. We can only detect indirectly these planets because they disturb the star. They transit, so they took some of the light of the star, and you notice that, or they made the star wobble. And so these methods for planet detection of this size are indirect. Some bigger planets, younger planets, and bigger and farther from the star, you can actually see the planet as a dot in pictures, and that's amazing. But smaller ones, you can just get, because eventually we will be able to see them individually. So you can see it, you know they exist indirectly. So the only correct thing in this picture is about their size compared to Earth, things that we can know. But how much water, how much atmosphere, that's something, that's a wild guess so far. And we can divide here the planets in different categories for reference in terms of how many planets. We can divide here, we might have tidal lock planets, always facing the same face to the star, so it will overheat, like the nighttime will take all the water and make it ice. And probably they will have a layer in between of water between the desert and the light side and the nighttime. But if you don't have that much water, you know what will happen is that you won't have enough water to create rain. You don't have rain, you don't create forests. You don't create forests, you don't support large animals. No large animals, no intelligent life. So for that, if you want a planet like Earth, you have to have all these classical elements in abundance. And you need to, and that will only happen if you have a continent with rain. So desert planets, just like Mars, but with good temperatures, they will have like rivers, like lakes, small bodies of water. But still, it will be a desert planet everywhere. So don't expect here probably not complex life like animals, but microbial life can do with a little water. Ocean planets has a lot of water, and you might anticipate, oh, then so we might have their whales or something, fishes, and no, this is not good because you don't have land areas, so you don't have those nutrients that are only available in the crust to provide that nutrients to the ocean. So they will be diluted at the bottom. So will be a ocean much more diluted than the terrestrial. So probably that it won't be able to support even fish, just microbial life. So not good anyway. So if you want then a planet just like Earth, you don't have, it has to have not that too much water, not that little water. You need continents, and you need, for that water, you can have rain and then create forests and so support a large biosphere. So that's the trick to have a planet. So all these categories, first category of planet could be habitable in terms of supporting at least microbial life. But if you want something, animals, an intelligent life, then it's this class. So the issue here is that all these planets that we are discovering, we don't know yet which one is in each category. So some might be tidal lock, probably many, because they're around red dwarf stars and around this kind of star, the planets are very close. They have to be very close because just to get enough heat to support liquid water, but also the gravity dominates and then makes the planet phase. So many are tidal lock, so like this, but some probably are desert or oceans. So we don't know yet which one is Earth like between all this sample. And it should be rare case.
Sweet. So I think we'll pause here for our first round of questions from the audience. If you have a question, please click on the Q&A at the bottom of your screen and type it out. If you would like to ask your question out loud, please use the raise your hand function, also at the bottom of the screen. So we have one from Laura. Thank you for doing this talk, Dr. Mendez. What do you think of the recent discovery of phosphine on Venus? Do you think it is more likely a product of something happening on the surface or in the atmosphere?
So it was announced 1 week, 2 weeks ago that phosphine gas was present in the atmosphere of Venus. And so far, phosphine is believed to only be produced by a biological process like on Earth. And it can be produced artificially on Earth, but you have certain conditions, and it can be also produced naturally, but like in the planet Jupiter, it's available in the planet Jupiter and Saturn there, but it's produced deep in the interior of the planet with high temperatures and pressure, much higher than what Venus can provide. Even that it has a high pressure environment at the surface, no, it's much higher pressure. So the only way that is believed so far to create phosphine are conditions in a planet just like Earth, or not that similar like Venus, is so far a biological process. But I would say that it's surprising for that a biological process happening in the clouds of Venus. As I mentioned before, I studied the habitability of clouds, and compared to any environment on Earth, is the worst environment in terms of to support a large biomass. And in the clouds of Venus, to have this environment support life, and then the motion of the atmosphere, the clouds, the system eventually will be going down a higher temperature and will move up. So I think that it won't be stable enough to support a ecosystem. It will sterilize eventually the system if you put life there, because those clouds temperature is about 60 kilometers. You have the right temperature and pressure, but it's in motion because it's so dynamic. So I don't think it will support. So my guess is that that phosphine is produced abiotically, So some other process, not life. And that's the big deal now. Just one, first, to make sure that we're detecting phosphine. So far, it's phosphine. Then that we are right about the biology part. And so maybe it's produced something. And there are some things already people thinking about that it might be produced something chemically and those conditions. And but I think personally that not life at all. Gomer.
So our next question is from Emma. Some of the potentially habitable planets have the same first name, TRAPPIST or Kepler. Does this mean that they are found near each other in space?
Oh, no, those only the name of the mission or the discovery. That's a catalog name. So for example, Kepler is observing a particular region in the sky. So in terms of the region of the sky, most of the Kepler planets are in a spot in the sky. But some planets are closer and farther. It's looking at that region. So for example, TRAPPIST is a particular name of the observatory that detected. So you will have, and there are many catalog names. So many of these planets are known by different names too. It's a maybe 10 or 15 names for, but those are the most popular name by the missions or the discoverer. So Gliss is another catalog name. That's the old name for the stars. Remember, these names are the name of the stars, and we add the actual name of the planet is a letter. It's B, C, D, or so on, up to 8, or the largest system so far is 8 planets. But so most are 1 or 2 planets. So B is C, and there's no A is for the star. So this is the name of the star with so only a few planets have formal names.
So our next question leads us into the next round of questions from an anonymous attendee. What is the reasoning behind looking for current Earth-like conditions versus the conditions of Earth billions of years ago?
Well, actually, people are looking everything. They're not looking only, even looking at life as we don't know it, because that's hard just to predict different conditions and different environments that we don't have experience. But scientists are looking for all different conditions. And even if we are looking for the conditions that I mentioned that are our criteria for deciding is the planet habitable or not, those are conditions that are met with Earth a billion years ago. The issue is that we are aware that even if you have this planet match all the criteria, it could have atmosphere, a lot of atmosphere, or no atmosphere at all. It was stripped long ago by the star. Maybe it has a lot of water, less water, and you don't know the age. You know the age of the star. So you can usually you expect that planet to be having the same age. But the actual condition of the planet, you don't know. Maybe it evolves more slowly or faster than our terrestrial counterpart. So you are aware of those conditions, and people are looking at what gases or biosignature could tell that it has life like today, but even life before our planet was covered by oxygen in the atmosphere. So it was an anaerobic environment, and what kind of gases would tell you that it has life. So that's a hard time. And phosphine is is one of those gases that we believe before that, or still believe that it is a good indicator of life. And we were looking for that. We were planning to look phosphine and other gases, but phosphine in other exoplanets. Imagine that we didn't look at Venus, and we look at other exoplanets, another planet star, and we find phosphine, and then the headlines, we say, we found life. And we will be thinking about something like just like Earth, and it was probably just like Venus. And it's worse. People have doubt that now that is not an indicator of life. So is very hard, very confusing. And now, so it is good that this detection of Venus is just a reality check that you have to be very careful for, and it's a complex thing.
So are we able to get to any other habitable planets? Are they within our reach?
Actually, no, and I will tell you more about that. They are far away. So far, we can look at them, and we can explore the solar system, and it will take a very, very long time to learn more about them. But I think in the next sections, I will tell you how long it will take.
So let's get into our next section. And could you tell us what would be the steps that you have to go through to know for sure if a planet is habitable?
Let me share my screen here. I think I answered that, Chris, with this picture, the steps to.
Yeah. How about, are we able to get to any in our lifetime?
Okay, so the issue here is to get to these planets is that they're far away. It's nothing like traveling in the solar system. You can travel to Mars by taking 6 months. You can travel to Pluto in 10 years. So, and that's quite easy. The issue is that stars are very far away, even the nearest stars. Light takes 4.3 years just to go to and we are traveling at too slow compared to the speed of light. So that means that in our current technology, we can go to these planets, but it will take our current technology about 70,000 years just to go to the nearest star. So that's a long time. So we cannot wait a mission. We can do it with the push. So the issue here is you have to push it faster, to move faster, to reach. But if you want to push it just to go faster, then you will have to spend a lot of energy. And when you start to calculate how big you have to make this rocket just to go to the A to B, then you realize that forget it. It's a massive structure of fuel of a rocket or a system just to go, let's say, in 10 or 20 years with a typical probe. People are thinking like, maybe there is some way to bypass that if we made the spaceship very small, like a chip with a camera. Then we may be able to produce enough energy, like by laser pulses from Earth, just to push by laser these. But I doubt that we have still the technology to make something that small and reliable. And that might take 30 years, 20 years, and that's acceptable. But you won't be able to do much with those. But there's a trick for that I would like to discuss later on.
So do you think that we will have to utilize some of these planets at some point in our future as humans?
Oh, probably the solar system. We will travel through the whole solar system, and at some point we say, do we need to go elsewhere? Maybe we have everything here. And yes, of course, we will do it because we are curious. But that will take so long. It's such a big challenge to travel through the stars. There are so many issues. And I can only think you build AI, artificial intelligence machines, and they just saw those machines in the void for probably 100 years. That will be your first attempt, and they will take you back. And probably you will have to also, by that time, just manage how to extend the life of people also, organic life, I mean, just to live not only 100, maybe 200 years. And so any alien life form that is capable to travel to the star, I expect to have a lot of knowledge and a lot of science. It's not that simple as science fiction. You just build your ship and just go on the ship and just go your way there, like randomly, like you don't know anything and just exploring. No, no, no. You have to be a good navigator. You have to be exploring the cosmos for a long time just to be a traveling through the stars. And it requires a lot of technology and science and knowledge to do so if you personally want to travel.
Okay, so I think we can take another pause here for some questions from the audience. We have a question from Catherine. Can habitable characteristics in a planet change over time? So could a planet become habitable over time?
Definitely. There's even Earth, the conditions in our own planet just change through time. So at some point, it was habitable, but it became better and better in terms of how much biomass. So it's not as simple as say that the planet is habitable, but how good is this habitability? And conditions can go right, but they can go wrong. And I would say that Venus and Mars are examples that things went wrong, because we believe that Venus long ago had an ocean, had enough water to have an ocean, and it was too close to the sun, so it lost all that water. But Mars was small. It has probably had an ocean also in the north, but it was small, even that it was farther away, colder, so it should trap that water, but the problem, it was so small. And that water just was stripped away by the interaction with the sun. So still some water in the crust, but most of the water in the atmosphere was lost, and it became just colder and colder. So those are big examples that in their past, we believe they have better conditions for life. We know that Mars had running water, a lot of evidence for that long ago. Like when the time that life was starting on our planet, Mars was fine and probably better than Earth at that point. But then they went wrong other way. So planet Earth has been mostly good, not that good, but mostly good. At some point, it was things getting better. And then probably now with the interaction of the human, then it's getting worse.
Our next audience question is, with Mars being the next possible habitable planet, is Mars or Venus closer to get to in terms of travel time?
What was the question again?
Is Mars or Venus closer to get to in terms of travel time?
Oh, Venus and Mars, they're really close. Mars is 6 months, but people don't realize that Venus is a little bit closer than Mars. But Mars had all the attention until a few weeks ago that Mars was even that Venus was long ago called the sister planet, because size, we were looking only at their size and similarity and that, but now we have realized the atmosphere is just a hell. So not that similar. So Mars is more similar to Earth than, at least the surface is more similar. Then so all the attention has been to Mars, even that is a little bit farther. It's definitely also much easier to explore than having the missions going to Venus at the surface, where the pressures and the temperature are too high to probably crush your your mission have to resist those temperature and pressures. And the only good environment that is the cloud tops that are now believed to have conditions for life. And so that might shift things, but I don't know for how long.
Janelle asks, is there something we could do to a planet to induce habitability? And if we can, should we?
Oh, that's the big question of terraforming a planet. And the issue here is, this is a very important point. And you have to, if you want to, there's two options. Life is out there, or there's no life out there. And each has the advantage or not. Imagine that life is out there, and that means that you have to share the space. And I mean even microbial life. Let's say there's microbial life on Mars, then you are entitled to protect that, just to study it, just to make sure you don't contaminate or it contaminates you. So you have to be very careful even for microbial life. Not talking even about complex animal or aliens, movie like Aliens. No. Even microbial life, you have to be very careful if life is out there. So that's a big issue. But imagine that we can somehow be sure that there is no life at all. So that sounds sad, that's scary also. But in the positive side, you can say that, well, the universe is ours to explore. We don't have any restraint to explore Mars, to go and trash the planet like we did on Earth, because there is no life there until we go over there. And so each has its advantage or unknown. So we have to make a decision on what and what we're gonna do. And we need the space eventually to move forward. And it will be hard to make this planet just say, okay, don't go over, because we want to respect the quality of any other body. And so we don't want to explore anymore. That would be hard to do. So we will have to probably make laws and more laws and requirements just to explore the solar system, and to be more careful with that. We need to mature a lot. I don't think that we have to go slowly, and so that's a big ethical question. We have to go slow on this one. We are very careful.
Christina writes, I have read that some lichens can survive for some time in space. Is it possible some life on Earth came from elsewhere? And if so, from where?
Okay, yeah, that's the problem of panspermia, of light coming, for example, from asteroids or fell down Earth and meteorite and probably inseminate. We don't know. So in this problem of astrobiology searching for life, and many people are so obsessed of searching for life elsewhere. Actually, in astrobiology, the important thing is to understand life, starting with your own life. And so extraterrestrial life is not required, because you just want to make the connection of our life with space. And probably eventually you find out that your origins are bound to somewhere else in the universe. Maybe it was producing planets in those exoplanets and have been traveling through all the galaxy for millions or billions of years. And just when it finds a good planet, then it flourish, not like Venus or Mars, but like Earth. Then maybe that's the story. And there is no extraterrestrial life at all. And that would be still exciting to know. So this is very important to know, this connection between life and the rest of the universe, and the possibility of panspermia. because it tells you about your origins. And when you know more about your past, you can make better decisions about your future.
So we'll get back into our regular sections now for our final section. What parts of your research are you most excited about?
Okay, let me show you. In this, let me go. I'm gonna show you a very nice slide. Oh, okay. Technical issues, no problem. Let me show you here. Okay. So doing this type of research, okay, so definitely I am totally excited about the kind of research we are doing. Mostly, I like to do more theoretical work more than experimental work. I enjoy both, but more theoretical work. But I also like to combine this with art. So I used to draw as a kid, and then eventually stopped because there was no need for me to draw anything at all. It was just like a hobby, and I was studying. But then with this process of creating this exoplanet catalogs, and then this field that there is no image at all of this planet. So that was for me to go back and go to the drawing board. And in 2016, we wrote a book, a very pictorial book with, and this portrait here, I made this portrait here. I now draw with a computer. No, it's not only by hand anymore, but a computer. So I like to do that. So that has been very exciting for me. And we will be able to, many of these images, I've been going through different TV shows and programs, like our work, in this case, our scientific work was consulted by different series like Cosmos and Human Universe. Those are documentaries. And more recently, One Strange Rock. That's also our research work. So we appreciate that not only our scientific work, also our art is also, and I will stimulate my students just to try to combine somehow your artistic side with science.
And your research at the Arecibo Observatory, what type of work are you doing there with that telescope?
Well, the Arecibo Observatory, everybody knows that the Arecibo Observatory observes the universe, stars, galaxy, but it also observes asteroid, moons, and planets because it has the radar capability. It's just able to send signals that bounce back. And it was used to do the first map of Venus in the 80s. That was done by the Arecibo Observatory because it has a thick cloud and nobody knew how was the surface. So that was done by the Arecibo. You need radar for that. It's not only that your radio signal goes to you. Arecibo also do atmosphere analysis of the ionosphere. So that's something, so they do some atmospheric science and planetary science. But most radio telescopes only do the astronomy science. And now we know that the FAST telescope in China, which is a little bigger than the Arecibo. Arecibo is 300 meters diameter. FAST is 500 meters. It can only do astronomy science. It cannot do planetary science. It cannot do this atmospheric science. So it's more versatile, very versatile, the Arecibo Observatory. And it's still the biggest radar. In this radar mode that you can send signal, if you need to send a signal into space, and you need to pick what will be the biggest radar to set, this is still Arecibo, because others are smaller. And so that's good. And what I want to do is with Arecibo is to the exoplanets. So it's interesting to know that the first exoplanet was detected by the Arecibo Observatory around a pulsar planet in 1992. That was totally unexpected because those pulsars are stars that exploded and when as a supernova, and when they exploded, the left nucleus is a pulsar star. It's a dense core after the explosion of the supernova. And you expect in that process that any planet at all will be stripped away, but no, it has, there are about 2 or 3 pulsars that have been detected with planets. And we now believe that those planets were formed after the explosion. So after the explosion of the supernova, that remnant material now contribute to create new planets. So that was discovered at the Arecibo Observatory. The Arecibo Observatory also observes brown dwarfs. These are in between planets and stars. They are not planets, they are not stars. This is the in-between system. And they have been detected in radio, for instance. They are not before, they have been detected by other observatories. But Arecibo was the first one detected in the radio. So radio emission is a natural process. Many people associate radio with some intelligence, somebody saying, no, it's light. It's light in other frequencies. So many of these objects naturally emit radio, and you're able to detect those natural emissions of radio. So that's why I am using the Arecibo Observatory to observe a few stars, but those stars has potentially habitable planets, a few of the stars that we have in our catalog, and we're looking through them just to see how good or bad is the space environment. If we see the star is very active, that's a bad star for a life, for any life in the planet. If we see the star is quiet, then we can say, okay, good, that planet probably still have its atmosphere. I will know to know if the planet has the atmosphere directly, but we cannot measure that yet. So the only way to indirectly measure it is how active is the star. So we are looking that to the Arecibo Observatory in our research.
So I have a fun question for you here now. Are you able to detect signals from any extraterrestrial civilizations from Arecibo?
Okay, people have been doing that, trying to do that since the 1960s. Frank Drake was the first scientist that tried that with a telescope a small telescope in the US. And it was tried in the 90s and the early 2000s with Arecibo, being the most sensitive radio telescope at that time. And there was nothing. So something is telling you right now, people are get mad that we are not detecting life at all. And well, we are detecting that so far, like we are alone. Because it's hard to detect anything, and we are not detecting so far any life. And in our project, because we are looking at the star, and our field of view will take anything from the star and any of the planets. So we have a large field of view from Arecibo. Then if one of those planets has any intelligent life transmitting at us, probably more high intensity than we usually do on Earth, probably on purpose, then we should be able to detect. And that's why we have now a new program to also search for any indication of artificial transmission also in our signals. So we can have all this data that we're looking only for things from the star. And now we will have a student looking also to, maybe there's something artificial in there because you're already looking at it. So, and you're looking at the right stars with the right planets. So maybe there's something. So we will try to do that. At least we were able to constrain that, okay, nothing is emitting from that star, at least with this intensity. So if there is something, it should be less intense than this. Is there, is anything. So we were able at least to have, to tell something, no detection. So detections and no detections are good. You are mapping the habitable universe, and it's not only finding life, it's finding places that, okay, they are not okay for life.
Okay, so we have a couple more broader questions for you before we end. Why did you decide to go into this field?
Well, I am not sure. It was, as far as I remember, I love astronomy, probably because I grew up in the deep in Puerto Rico. There were not too much light. Now it's too busy, but when I grew up, and I had a beautiful sky, and probably that black sky full of stars was an inspiration. And I asked for a telescope as a present. So I got a telescope. So I asked for a computer. And I at that time, and I got the computer. So I started to learn then to observe, to make map of stars, to compute the positions with the computer. So that was involving in early life. And I was drawing also, as I said before, but I was naturally more fascinated with a career in astronomy. My mom and dad thought that maybe I wanted to be an astronaut because all that fascination. And no, I don't like heights. I don't like airplanes, not rockets. So no. I just want to look at them and to learn about them, not to go there.
So science, like other academic fields, has been criticized for a lack of diversity and inclusion. What does diversity and inclusion in the sciences mean to you?
Well, it's hard because we try to diversify in all aspects, not only in gender, but also involve persons from different fields, different cultures. That's very important because you need to try to get all the help you can get and not exclude. And I've been lucky to be involved with a lot of people from different backgrounds. And that's, I think, some key just to learn. When you have a diverse group with different ideas, that's wonderful. And people reading the news and sharing the news, and they have a different perspective of this discovery and that discovery. That's something very important to have.
Okay, so we're now just a little after 7. So some of our audience may need to leave. So thank you so much, Dr. Mendez, for being here today. Are you able to stick around for a couple more audience questions?
Oh, yes, definitely. And I show you my students right now. This is a very diverse group of students from Puerto Rico. And we have also colleagues from elsewhere.
Carissa, if I'm pronouncing your name correctly, writes, do you think there is a microbial life on Europa or Enceladus? If so, what would this mean?
I think that microbial life in Europa and Enceladus, Europa is a moon of Jupiter and Enceladus is a moon of Saturn. And we believe that Europa has a big ocean, probably 100 kilometers deep. For reference and comparison, the average depth of our ocean is 4 kilometers, but there is a lot of water there. And I choose, I have a slide that can share that. Oh. It has this comparison. Let me show you. Oops. Uh-huh. So this is Earth. That's all the water on Earth make as a bubble. So it's right to call our planet Earth and not ocean, because even like it looks like it has more water than Earth. It's mostly rock. This is a comparison Mars, and this is the ocean we believe it had in the past. So to the scale about the same amount of water, but when you go farther away, and these are the moons, 2 moons of Jupiter, this is how much water Europa has. And this is water, liquid water. And here you have a 10 kilometers, about 10 kilometers deep ice. And below that ice, probably that 100 kilometers deep liquid water. So everybody think, okay, so a lot of water, the baby fish, something whales. But if you go back at the analogy of the classical elements, and you think about this ocean, and you say, okay, how much wind, which is the atmosphere? It doesn't have an atmosphere. So there are little dissolved gases there. Okay, so you have the water, it's fine there. But let's say how much earth it has. So that will provide the nutrients. So the rock is deep in that ocean over there. So it's too deep. And so it means that that water will be much more diluted. And what will be the energy? Not sunlight. So you will rely on only chemical energy, and that will be much less. So that ocean is dark and definitely much worse than anything on Earth. Even the deepest trench, the Mariana Trench, 11 kilometers deep, that's worse. And when you look at those worst places, you don't find at all that too much life, only a lot of microbial life. So we probably think that this system, if any life at all could be supported there, it would only be microbial life. And that's fine, because microbial life needs a little bit of those ingredients, and they're available in theory over there. So I think that's a good possibility, but thinking about something big, I doubt it. And that's the case for also for the moon of Saturn, Titan. It has a lot more water below the deep atmosphere, and some ice and rock. And Enceladus is this small, but it has a lot of water compared to its size. So there's good chances for those bodies. We need to explore those bodies, definitely.
Laura asks, what do you think about possibility of, oh, I'm sorry, life on Titan, but you just addressed that. Janelle asks, what resources, podcasts, books, etc., would you suggest for someone who is intrigued by these subjects but doesn't have a background in astronomy? P.S. Thank you for your talk. It was great.
Oh, good. Thank you. Okay, I recommend just a form, try to learn more and, learn the field. The general term that you have to look is astrobiology. Astrobiology is the study of life in the universe. And I said before, when I said study of life in the universe, including your life, starting with your life. Because you say, but what's the connection to space? Well, the origin of life might be connected to space. As before, we was discussing panspermia. And the planetary formation decides the origin of your planet and then of your life. Then you will have that the planet will evolve, and that your life has to be adapted to that environment, and you will have impacts from a space that might change the habitability of your planet and might cause extinctions. So there is a lot of connection even for life on Earth with space. So that's in astrobiology, people dedicate to study life and in connection to space. And that's fine, totally fine. And probably the other half of astrobiology are worried about life elsewhere. But even if you're worried about life elsewhere, you have to learn life on Earth, because that's an example and that's a comparison, just to, if you find anything else, just to tell, is that related or not to life on Earth? You have to know your life. And there are two articles, there are research, like a review papers that are very good in this topic. They are called the astrobiology primers. There, if you look for in Google astrobiology primer, there is one from 2006, and there is another one 2016. And I prefer the 2006, the organization format of the paper, but obviously the 2016 version, it has more recent content. So they're review papers, and they're very general, but also they link to the scientific papers and on the topic. So that will give you an idea of what astrobiology does and who is doing the astrobiology and how you can get involved, because astrobiology is people working in any field.
Allison writes, thank you for a wonderful talk, Dr. Mendez. How do atmospheres form? Do all planets have atmospheres? Is a protective atmosphere an important ingredient for potential habitable planets?
Oh, definitely. And also depending on the life that you are, if you, as I said before, if you want planets just like Earth, able to support complex life, then you need definitely your atmosphere. And that atmosphere needs your, to have oxygen in particular. And why oxygen and not other gases, or beyond other gases? Because if you want animal life, the animal life needs a lot of energy, to consume a lot of energy, and oxygen provides that energy. If you don't have a planet that has enough oxygen, then it's probably only good for microbial life. Also, if you're interested in intelligent life, you also need oxygen, because you know what? If this intelligent life builds technology, you need to melt metals. And for that, you will need fire. And for fire, you need oxygen. So everything tells you, if you are thinking about a planet capable of sustaining not only life, complex life, animal life, or intelligent life that builds technology, it will need oxygen. And that's, and also it will need also rain. So I'm sure, and let's joke about this, that if you find any alien, intelligent alien, and you can be sure that, okay, I know something about you. Your planet, you breathe oxygen. Definitely. The only way, you don't, unless your ship is built in or wood or stones, you don't need oxygen to make fire and melt. Definitely, you don't come from the ocean, deep ocean, like some science fiction. They cannot build technology, fire of the water. So, okay. So I can tell you that maybe you can have other gases in you that are bad for us in your planet, but you need oxygen, definitely. The other thing that I will know straight out of the unintelligent, that you know what rain is. Because I know your planet rains, and you know your planet has forests. Because is the only way to have enough biomass to support a large ecosystem for life to evolve eventually to animals and then to you. So definitely, you know what rain is. Your planet rains, and it has. So if the planet, if you are, so this is get more restrict and more similar, eerily similar to our planet. If you are considering intelligent life, if you're considering just animals, simple animals, then you might go more wild about the conditions of your planet. But that's something neat to think about.
Maybe we'll all be a little bit more optimistic next time it's raining out. So that'll be the end of our questions. Thank you so much, everyone, for coming. Thank you so much, Abel, for being here. Do you have any parting words for us?
What was that?
Do you have any parting words for us?
You mean last words? Okay. So yes, that as I said before, that this field of astrobiology needs a lot of knowledge. I know people are interested in extraterrestrial life, but when I started in this field, it was my very simple-minded focus on extraterrestrial life. And then the more you learn about this field, you tend to appreciate more your life. You appreciate more your planet. And now, even that I'm studying this field, I'm more interested in terrestrial life. I worry about what was its past, and especially what will be its future. And I know that understanding the universe, understanding the possibility of other lives, just tell, because that's right now the most important, your own life. Mm-hmm. Thank you. And thank you for having me. And it was it's a lot of fun. Thank you for the questions. That was great.
It was so great to have you. Have a great night, everyone.
Okay, bye-bye.